We have built machines that can diagnose rare diseases with startling accuracy, predict market crashes before they happen, and navigate chaotic city streets without human intervention. Yet if you ask the creators of these systems exactly how the machine arrived at its final conclusion, the answer is often a variation of, "We do not entirely know." This is the central paradox of modern artificial intelligence. We are handing over the keys to our most critical infrastructure to systems whose internal logic is fundamentally opaque to the human mind. This phenomenon is universally known as the black box problem. It describes a scenario where an AI system takes in vast amounts of data, performs complex calculations, and outputs a highly accurate decision, but the pathway between input and output remains hidden. The user can see what the model decided, but the underlying reasoning is completely invisible. As artificial intelligence moves out of the laboratory and into hospitals, courtrooms, and banks, this lack of transparency transforms from a minor academic puzzle into a profound societal vulnerability. The root of this opacity lies in the architecture of deep neural networks. These systems are loosely inspired by the human brain, consisting of multiple layers of interconnected nodes, or artificial neurons. When a deep learning model is trained on massive datasets, it adjusts millions or even billions of internal parameters to minimize errors. These adjustments happen across countless nonlinear interactions, creating a web of mathematical relationships so vast and intricate that no human can trace the exact sequence of calculations that led to a specific output. The network simply becomes too complex for its own creators to reverse engineer. To understand the gravity of this issue, consider a highly advanced medical diagnostic AI. Imagine a system trained on millions of medical scans that flags a routine X-ray for early-stage lung cancer. The doctor looking at the scan sees nothing abnormal. If the AI is a black box, the physician is left with an impossible choice. They must either ignore the highly accurate machine, potentially missing a fatal tumor, or subject the patient to invasive, dangerous biopsies based purely on blind faith in an algorithm. Without a clear explanation of what the technology detected, the medical professional cannot independently verify the diagnosis. This same dilemma fractures the financial industry. Banks increasingly rely on machine learning to determine creditworthiness and approve loans. If a traditional rules-based system denies a mortgage, the bank can point to a specific reason, like a high debt-to-income ratio. But when a deep learning model denies a loan, the rejection might stem from a convoluted correlation of hundreds of seemingly unrelated data points. If the system has inadvertently learned biased patterns from historical data, the bank could be committing systemic discrimination without even realizing it. The opaque nature of the system hides the bias, making accountability impossible. The core issue here is trust. For society to fully integrate these systems into high-stakes environments, humans must be able to trust the machine's decisions. Trust requires transparency, and transparency requires a translation of machine logic into human reasoning. We cannot simply accept an output because the statistical probability of accuracy is high. We need to know the why. This urgent need has birthed a rapidly growing subfield known as Explainable AI, or XAI. The quest for explainable AI is the scientific effort to crack open the black box and force these complex models to show their work. XI seeks to develop tools, techniques, and entirely new model architectures that provide human-readable explanations for algorithmic decisions. It is about bridging the cognitive gap between the hyperdimensional mathematics of a neural network and the linear causal reasoning of the human brain. One of the foundational techniques in this quest is called LIME, which stands for Local Interpretable Model Agnostic Explanations. LIME operates on a clever premise. Instead of trying to explain the entire massive neural network all at once, it focuses on explaining a single specific decision. If an AI classifies an image as a wolf, LIME slightly alters the image, hiding different pixels, and runs it through the model again and again. By observing how these small changes affect the final prediction, LIME can highlight exactly which parts of the image were most important to the model's decision. It creates a simplified, localized map of the AI's reasoning. Another powerful tool in the XI arsenal is SHAP, or Shapley Additive Explanations. SHAP borrows a concept from cooperative game theory to assign a specific value to every single input feature, measuring exactly how much that feature contributed to the final outcome. If a financial model predicts a high risk of default, SHAP can break down the prediction and show that the applicant's recent credit inquiries increased the risk score by 15%, while their long employment history decreased it by 5%. It provides a mathematically rigorous accounting of the model's internal priorities. While tools like LIME and SHAP represent massive leaps forward in AI interpretability, they are essentially post hoc explanations. They are separate algorithms trying to guess what the primary algorithm was doing. This introduces a new layer of uncertainty. Are we actually seeing the true reasoning of the model, or are we just seeing a plausible rationalization generated after the fact? An explanation that is merely an approximation can sometimes be more dangerous than no explanation at all, as it provides a false sense of security to the humans relying on the system. This brings developers to the most frustrating hurdle in the field, the inherent trade-off between model performance and interpretability. In the current landscape of machine learning, there is a distinct inverse relationship between how accurate a model is and how easy it is to understand. The most transparent models, like linear regression or simple decision trees, are highly interpretable. You can trace their logic on a single sheet of paper. However, these simple models struggle to process complex, unstructured data like images, audio, or human language. Conversely, the models that excel at these complex tasks are inherently uninterpretable. Their power comes from their complexity, and their complexity is exactly what makes them unreadable. When companies choose to deploy an AI system now, they are often forced to choose between a highly accurate system they cannot understand and a fully transparent system that performs poorly. In competitive markets, accuracy almost always wins, pushing transparency to the sidelines. Consider the autonomous vehicle industry. Self-driving cars rely on massive, opaque vision models to distinguish between a pedestrian, a stop sign, and a shadow. The priority is absolute, immediate accuracy to prevent fatal collisions. Engineers cannot afford to use a simpler, explainable model if it means the car takes a fraction of a second longer to identify a child running into the street. In this scenario, the lack of transparency is accepted as the cost of doing business, even if it means crash investigators will struggle to understand exactly why a tragic accident occurred. However, governments and regulatory bodies are no longer willing to accept this trade-off. The legal landscape is shifting rapidly to demand algorithmic accountability. Frameworks like the European Union's General Data Protection Regulation have introduced language that implies a right to explanation for citizens impacted by automated decision-making. More recently, comprehensive legislation like the EU AI Act classifies certain AI systems as high risk, mandating strict transparency and human oversight requirements before they can be deployed in the market. These regulatory mandates are forcing a structural shift in how artificial intelligence is developed. It is no longer enough for an AI to simply be accurate, it must be legally defensible. If a government agency uses an algorithm to distribute social benefits or a judicial system uses one to recommend bail, those institutions must be able to prove that the system's decisions are fair, unbiased, and grounded in logical reasoning. The black box is incompatible with the foundational principles of due process and civil rights. The ethical stakes of AI interpretability go far beyond mere regulatory compliance. We are building systems that will ultimately shape human destiny, dictating who gets hired, who gets medical treatment, and who is deemed a threat. If we cannot understand the intelligence we are creating, we cannot control it. The danger is not necessarily a malicious AI uprising, but rather a slow, silent surrender of human agency to statistical models that optimize for efficiency at the expense of human values. To prevent this surrender, the frontier of XAI research is shifting away from post hoc explanations and toward developing inherently interpretable models. Researchers are attempting to build deep learning architectures that are transparent by design, constructing networks where individual layers or nodes correspond to specific human understandable concepts. Imagine a medical AI where one specific part of the network only looks for tissue density and another only looks for shape abnormalities, allowing the doctor to see exactly which physical traits triggered the diagnosis. Yet this pursuit forces us to confront a humbling philosophical question. Is the universe inherently understandable to the human mind? We demand that artificial intelligence explain its reasoning in terms we can comprehend. But what if the patterns these machines discover in massive data sets are simply too complex, too hyperdimensional for the human brain to process? We may be building an intelligence that operates on a level of reality we are biologically incapable of visualizing. The challenge of explainable AI is not just a technical hurdle, it is the defining friction point in our relationship with thinking machines. As we continue to integrate these powerful systems into the fabric of society, the demand for transparency will only intensify. We are no longer just building tools, we are building partners in decision-making. And any true partnership requires communication, understanding, and the ability to look inside the logic of the other and see exactly why a choice was made.